Today's lecture is on warning flip-flop design and operation. It is a part of module 3. So, first we will discuss the challenges in near threshold voltage or low voltage flip-flops, and to address these challenges, what are the important near threshold voltage flip-flops which are proposed, and also many of them are in use. So, today we will discuss error detection and correction flip-flop. As you can see, this is the distribution, and distribution of Foundry library, a standard cell library from Foundry, is the distribution of delays is quite large. Standard deviation is quite large compared to typical nominal voltage operation. And the reason is that you have a lot of process and voltage and temperature related variability, and because of the small headroom, VDD minus VTH is very small. In fact, it could be negative, positive. In near threshold regime, it could be either negative or positive, and VDD minus VTH, nevertheless, whether it is negative or positive is very small. So, any variability in threshold voltage or supply voltage or even temperature, temperature changes the threshold voltage. So, you will find that the delays vary significantly. So, therefore, the standard deviation of delays would be much larger at in low for low voltage operation compared to the nominal voltage operation, and that is what we are seeing here. This is this red distribution is, you can see it is quite much larger, and it is for a standard cell library which is designed and used in nominal voltage operation. So, the same standard cell library when you use in near threshold voltage operation, this shows the standard deviation. So, what does this do? So, you have because of this, the capture flip flops in a pipelined architecture, for example, the capture flip flops setup time violation can be significant. Or to overcome this problem, if you use less number of and to count and to avoid margins, okay, pipelined architecture, capture flip flops setup time violation, and to counter this problem, if the logic depth is reduced, hold time violations can result. So, if the logic depth is reduced, what would happen? So, to counter the problem of setup time violation, if you reduce the logic depth significantly and play with margins, then it may so happen that whenever the delays are very small, you may have hold time violation. The next cycle's data may come before the hold time of the capture flip flop is passed. So, you may have hold time violation in the capture flip flop. This is another thing that is being shown. So, in Monte Carlo simulations of a large number of samples, the critical path delays, you can see that the critical path delay distribution is such large. So, it can be in this range or in this range. So, it is quite a large critical path delay distribution. So, it is for the same critical path. So, it can be in the range of 4 nanoseconds, and here it is in the range of 14, 16 nanoseconds. So, that is quite a large distribution of the critical path delays that you are able to see for the worst case and best case scenarios. So, it is coming from around 7, the variation is from around say 7 nanoseconds to 16 nanoseconds. So, that is quite significant. So, these variations, it is very hard to handle using design techniques. So, what are the major issues? One is variability, the other one is noise margins, because your supply voltages are smaller. So, noise margins are again smaller, and to overcome these issues with variabilities, design complexity can be increased, and reliability of circuit operation is affected. One of the methods to overcome this issue is to use a warning latch, okay, or a shadow latch, which would do an error correction whenever there is a violation of say setup time. So, here the basic idea is like this is the random logic and the input is coming here. This is the main flip flop. The shadow flip flop has a delayed clock compared to the main flip flop. So, locally generated delayed clock it would have. Now, if the shadow flip flop finds a, so the data would come from here, and if there is a setup time violation. So, this is a concept diagram, the implementation could be of several types. So, now this is data which comes to the main flip flop, and after the setup time window is over, at the suppose again the data comes. So, shadow latch has a delayed clock, and therefore, it would latch the value of the changed value of data correctly. Main flip flop setup time violation is happening. So, it may not capture the data correctly. Okay. So, in such a case you will have the output to be 1, and that would make the shadow latch output to be given to the main flip flop, and you would get the correct output of the main flip flop. So, this how is this implemented? One very popular circuit we will look at. Here is an implementation of the razor concept. So, this is a master latch, okay, and instead of an inverter, here you have this multiplexer, inverting multiplexer, and this is slave stage, and here you have the shadow latch which has a delayed clock, okay, compared to the main clock, and here you have a metastability detector. So, I will now explain how it functions. Suppose the operation is normal, there is no error, there is no setup time violation. So, in that case the data comes here, it is latched here, okay, and the same data for the delayed clock also. So, you delay the clock in such a manner that setup time violation could be handled. In the sense, you may, there could be several ways, but one of the ways is that you may delay it by the estimated setup time, for example. Okay. There could be other ways also, like one could delay it to half the clock cycle. But in this case, let us consider the example where you delay it by the setup time of the estimated setup time of the flip flop. So, here you have delayed this, delayed the clock. So, if there is no setup time violation in that, and also no hold time violation. So, in that case the shadow latch would also latch the same value as D, and the main latch would also latch the same value as D, okay. And after the clock transition, the shadow latch would be, after the clock transition, the clock goes from 0 to 1, the clock goes from 0 to 1, you would find that the shadow latch would become opaque, it would not conduct, main latch would also not conduct, but this latch would, slave latch would conduct, and the data would go out here, and it would be latched to data D, and you will have the same data here, same here. So, there is no error, you will find no error here, okay. And since there is no error, this would latch to, this would keep latched to Q, it would keep latched to Q. Suppose there is a setup time violation, then what would happen? This would latch to a wrong value, and because there is a setup time violation, this can latch to a wrong value QM, and but here you have taken care of the setup time violation by the clock period. So, clock delay, not clock period. So, this delayed clock is coming after a while. So, D is not latched, and initially D is not latched, okay. So, that is why QM, you would find, if you plot QM, you will find that you will find QM rises after the shadow latch has got the right value. So, now we have a setup time violation and therefore, QM could be different from QSH. QSH is after the, so there is a setup time violation, you can see that the data D is changing at the clock edge. So, there is a setup time violation here, and the delayed clock is able to handle delayed clock. With delayed clock, the shadow latch is able to capture the data. So, the shadow latch output is coming correct, coming is transitioning to 1 as it should, D is transitioning to 1. Okay. And when clock is transitioned opposite, then what happens is this slave latch also is now transparent, and therefore, once slave latch is transparent, this you detect that both these are different values, because the slave latch has taken data from a setup time violation. It could be flipped to a wrong value because there is a setup time violation, and as we had discussed in the previous lecture, if there is a setup time violation, metastability can result, and metastability can result in a wrong value being latched, because the metastability point, if the value of QM is at metastability point, it may flip to either VDD or 0 randomly. So, you could have had a flipped value here. So, that flipped value, suppose this is 1, this is 0. So, error is, so you have a 1 at the output of the XOR gate, and the suppose there is no metastability here, this is properly, it has gone to 0, but in a wrong, it's had latched to a wrong value, because there was metastability at QM, not at Q. Okay. So, it has, so because at QM, if there is a metastability, it can result in some transition, not, for example, if QM is to turn to VDD, but it has turned to inversion threshold voltage, we suppose VDD by 2. In that case, here you will have a voltage which is larger than VDD, VDD by 2. So, this may detect it as a 0, you may have a 0 here. So, you have a 0 coming in here, and you have a VDD coming in here, you have 1 at the output, that 1 at the output, and but you have a proper 0 here within noise margin. So, the metastability detector's task is that if Q is at a metastability value, say VDD by 2, then it should resolve, the output should be 1, and if Q is at a proper value, a proper logic value, either VDD or 0, then metastability detector should give a 0 here. Okay. So, suppose Q is wrongly latched to 0, proper logic 0. So, in that case, metastability detector would give a 0, but here you have a 1. So, therefore, error latch would give out a 1, and that 1 would turn the multiplexer to take this input, okay, the input QSH. So, when the clock turns 0, at that time, after a while, QM will resolve to the right value, correct value VDD, and the output Q would also turn to VDD after a while. So, how is this implemented? Let us see. So, you will have a multiplexer here. So, we are implementing it using a transmission gate multiplexer. The signal error underscore L goes here. This goes to the node I, where this is the node I. So, as far as possible, this path should be fast enough, so that Q is resolved to the right value at very fast. So, that would, if you increase the size of this, it would load the shadow latch. So, a careful design from here till the end of this point I, a careful design from this input to I must be done, so that the delays are small. So, now let us discuss the metastability detector. So, how does this metastability detector work? So, let us call this inverter 1, let us call this inverter 2, inverter 3, this node as N1, N2 and N3. Suppose inverter 1 has a Wp by Wn which is very small, extremely small. Suppose for a balanced inverter the Wp by Wn has a certain value. So, for inverter 1 the Wp by Wn can be 1/3 of it, for example. Likewise, for inverter 3 the value of Wp by Wn can be quite large, very large. Suppose it is double or 3 times the Wp by Wn that you choose for a balanced inverter. Now, with this let us see what happens when the value of Q, it can be wrongly latched, but it is a proper 0 or 1. Okay. So, let us see how the voltage transfer characteristics of inverter 1 and inverter 2 look like. Inverter 1. So, let us see for inverter 1. So, N1, for N1 Wp by Wn is very small. So, the voltage transfer characteristic would be okay, like this. So, your lower noise margin is quite small, okay. And for inverter 3 and 3, the output N 3, how will it look like? And suppose this is VDD by 2, which is close to V inversion, okay, or inversion threshold of the inverters. Or conventionally, so which is close to V inversion threshold of balanced inverters. So, whenever Q is a logic 0, so this will be like this value would be like VIL of the balanced inverter. This is like VOH of the balanced inverter. So, when Q is 0, logic 0, for the balanced inverter, we would find that N1 is 0, N1 is 0, okay. N2 is VDD, N3, I am sorry, N1 is VDD, N2 is 0 and N3 is VDD. So, out is 0. Okay. Likewise, when Q is proper logic VDD, logic 1, for the logic 1 for the balanced inverter, and 1 is 0 and 2 is VDD and 3 is 0. So, out is again 0, okay, as required. Now, let us look at the scenario where metastability is there. So, Q is now at close to VDD by 2, suppose. So, which is a metastability, which is close to metastability point of the balanced inverter. So, for inverter 1, this is interpreted as 0. So, for inverter 1, this would be interpreted as a input logic 1, as we can see. Okay. So, N1 would give a 0. Therefore, N2, which is a balanced inverter, would give a VDD at the output, give VDD at the output. Whereas, for inverter 2, since you are at VDD by 2, this is interpreted as input 0. For inverter 3, this is interpreted as input 0. So, its output is VDD. Therefore, out would have an output VDD. So, you have detected metastability. So, what is the function of metastability detector? What is the function of metastability detector? So, whenever there is metastability and Q has not resolved to either logic 0 or 1, the error signal, so this would result in E error, the signal error underscore L being VDD. So, the Razor flip flop would give out whenever there is Q and QSH are different, but both are having proper logic values within noise margins, error underscore L would be VDD. And if even if Q is not having a proper logic value within noise margins and it has some intermediate value, even then error underscore L is VDD. Now, let us look at what are the timing constraints one needs to follow. So, we are now discussing this capture flip flop, which is a Razor flip flop. So, every flip flop need not be a Razor flip flop. Wherever you have the apprehension because of some analysis, you know that there could be setup time violation. Suppose this is a critical path. So, then there could be setup time violation. So, you would place a Razor flip flop at the capture stage. So, suppose this is a Razor flip flop. So, what is the timing constraints that we should follow for race condition not to happen? So, the new data could be arriving. Suppose the random logic delay is such small that data D in 2 changes within the, suppose this is the whole time of the shadow latch and this is the delay. So, the data D in 2 changes within this delay and hold time within this time. So, in that case shadow latch may capture a wrong value, because the next cycle's value, next clock cycle's value may be ready at D in 2 before the whole time of the shadow latch is over. So, one should be careful and the delay of the combinational path should be, so delay of the random logic, combinational data path should be larger than or equal to the delay of the T delay plus T hold. So, this is T hold of the, suppose this is the whole time T hold of the shadow latch, and this is the delay of between the two clocks we call T delay. So, in this lecture we discussed the challenges in near threshold voltage circuits and the need for having to handle these challenges at a flip flop level, and we discussed an error detection and correction flip flop which is very popular, Razor flip flop. We discussed the various circuit components in it, its operation, its design principles. So, as a part of that we discussed metastability detector, and we also discussed the timing constraints associated with this Razor flip flop. Thank you.